Good morning, students. Well, it's Thursday, so hopefully everyone will be a little bit better attitude with the fact that the weekend is approaching and give you a little bit more flexibility. Always thought that mathematics was the friend of the weekend because, especially when I was an undergraduate and in grad school, having the time to do extra work when I didn't have to go to class was always a plus. But again, you have jobs and you have family obligations and other things, but at least you're not having to attend class. But now in our virtual world, everything's been turned upside down. So hopefully there's a respite for you on the weekend. Now, what I want to do is go back to the identities with the logarithms, the laws of logarithms, talk a little bit about those, and then segue into how we can actually make these new identities work with solving equations. We can solve basic equations using the definition of the logarithm and its equivalence to the exponential form. But what we want to be able to do is to apply some of the identities to be able to solve a richer variety of examples. So what I want to do first is go ahead and share my screen so we can talk about a couple of the identities that we did last class. Now, again, you will not find this material as difficult as that of the polynomials because it's integrated very nicely. Everything is pretty much the same thing. Polynomials can be very, very different. You know how the zeros can vary. You can have very different properties. So what we want to see with the logarithms is that the intimate relationship with their inverse function, the base A exponential, makes them really easy to work with, and we don't have as many options. So what I wanted to do was to just basically summarize a couple of identities that I gave you at the last class, and then show how we could actually show that they were valid and then use some of them. Now, what I've written here, I added a new one here that I want to share with you, but the power rule was one of the identities that we found that was actually kind of miraculous. That is not surprising, but still, a very useful result. If we take the base A logarithm of a power function, and that means we could replace x with a fixed base too. So x can vary or it can be fixed. So this is a very useful, flexible rule. What happens is that the power actually can move to a coefficient. So this gives the logarithm a very, very interesting characteristic that again makes it a very powerful tool in mathematics. When you study more calculus, you will, or actually more math in the calculus sequence, you will spend time with the logarithm and exponential functions. They're very important. Now, the first change of base that I gave you, and we're going to talk about why these are true. The first change of base I gave you was that for the logarithms. That is, say for instance, you're working a problem and you're in base A, but you'd like to change to base B. Well, the actual formula is fairly straightforward. That is, when you change to base B, you simply do a cosmetic change. You reverse the A into a B, but then the change of base factor is the log B base of the old base. So you take the base B logarithm of the A base. So this is easy to remember and makes the use of this fairly straightforward. Now, in a very similar vein, we can change bases based upon the exponential function. And this is just using the power rule. So for instance, we use the fact that the exponential function and the logarithm function are inverses. So we could write a to the x as b to the x log base b of a. That is, the x is just moved down by the power rule, but the b and the base b logarithm just absorb each other. But this is a very convenient way, just using the inverse relationship to get a change of base for the exponentials. Now, you might be thinking, I keep saying that the base E calculus is proven in your calculus sequence. And so if we use these change of base formulas in calculus, we can get calculus for any base. So one thing that's really useful is that in calculus, we'll say we have maybe a base 10, 10 to the x, we can use the natural logarithm. So we can say e to the x ln a. So this will be a formula that we will use widely in the calculus, just like the formula I gave you for the natural logarithm in the last section or the last lecture. So the idea is that you can change an exponential function to any base, and if you have a very distinguished base like the natural base, this proves to be very, very useful. And again, extends the calculus of the natural base to the calculus for any base. So the use of the logarithm here and the exponential function are very important. That is, we look at these as essential tools for studying the calculus. Now, before we do a couple of illustrations, I just want to write down why these are true. So for instance, if someone said, with what you know right now, could you motivate why the power rule is true? So first, what we want to do is we want to let z be the base, and use any letter you like, the base a logarithm of x, because all we have is the definition. And then of course we can cheat and use the exponent laws for the exponential function. I know this is a little bit circular because we're assuming a lot of things, but right now that's all we can do, and it will suffice for now. So now, what's a logarithm? A logarithm is the power of the base. So the power of a that equals x is z. So we have x equals a to the z power. What's a logarithm? Power of the base. So the power of a that equals x is z. A to the z equals x. And so now we have a way to write x to the r. So x to the r will equal a to the z raised to the r, which is a to the zr, or if you like, a to the rz. Either way, zr, rz, multiplication is commutative with real numbers, but now we have an exponential form in this particular case. That is, when you look at this, you're thinking, well, what would be how would we actually write this as a logarithm, so to speak? So when we actually do this particular setup here, we're thinking, okay, so how can we use what we already know to get something here? So now, equivalently, the base a logarithm of x to the r will just be the base a logarithm of this exponential term. But now this is like what we did last time. What power of a equals a to the rz? Well, just rz. These collapse. These are inverses. So this is just rz. But z is the base a logarithm of x. So we have r base a logarithm of x. And that's what we wanted to show. So indeed, if you take the base a logarithm of x to the r, that will be r times the base a logarithm of x. So the r can move in front, become a factor or a coefficient. So again, even though this is not the most maybe elegant way to prove this, with what we know, it does offer a system of deductive steps that gives us the result. And so at this point, we're happy to have it. So again, I always say use these identities to good help because they push the problem forward, so to speak. Now, for the change of base, so this one's taken care of. For the change of base, we'll do the same thing. Why? This one's self-explanatory. We don't have any proof to do there. It just is because of the inverse relationship. So here we're going to say let y equal, in this particular case, the base A logarithm of x. And what we're interested in doing is changing to base B. But again, just based upon the definition of the logarithm, what does this mean? Again, a logarithm is a power of the base. So the power of A that equals x is y. So x equals A to the y. And now, to introduce the base B logarithm, we simply take base B logarithms. So we will apply that here. So now we have the base B logarithm of x will equal the base B logarithm of A to the y. But now we have the power rule here. That is, I told you that any x will work. Namely, if we take x equal to A and fix it, it's still valid. So the y can come down. So now we can actually solve for y if we divide by the base B logarithm of A. So solve for y equals the base B logarithm of x divided by the base B logarithm of A. So even though the actual proof is very similar to the one we did here, it utilizes the concept of the definition of logarithm. So what we're finding in the pre-calculus context, when we think of the logarithm as the inverse of the exponential, that certainly gives us a very, very powerful technique for switching between the logarithmic and exponential form, which are equivalent. So when we get to calculus, we're not going to forget any of this. We're just going to start with the natural logarithm, show it's 1 to 1, and then move forward to get the inverse function later. So we'll do the reverse in calculus, but we're not going to forget any of this because all of this is valid. It's just that we will not arrive at these results in the same order that we have done in this class. So the idea here is when we just go through the basic ideas here, ladies and gentlemen, we're simply reviewing what it means to define the base A logarithm. And we always move from the logarithm form to the exponential form. And that's a basic construct. So a logarithm is a power of the base. A logarithm is a power of the base. If you understand that, you can do logarithms. If you do not, then you will come to grief. So that's why I'm always going to be very specific about this construct every time we use it, because it will push you to the next level. Now, with that, we want to do some examples utilizing some of these rules. So let's do some of that. And then what we want to do is see how we can do some more elaborate equations. So for instance, here's some problems that we can look at. For instance, say we just want to evaluate an expression using the laws of the logarithm. So we have log base 2 of 70 minus log base 2 of 2 minus log base 2 of 35. Now, what WebAssign will do, you know, WebAssign is always using the philosophy that every response is exact. Every response is exact, and every response is formatted according to the directions from WebAssign. So, unless, as you well know by this point, unless WebAssign says approximate to the nearest integer or a certain number of decimals, you give an exact response. That is given, always the case. There is no questioning that. Mathematics requires an exact response. That's just math in general. I'm not sure where that got lost, but we adhere to that philosophy. So when we look at this and WebAssign says evaluate, we're going to see if we can do this based upon the identities that we have. Now, first off, if you look here, this is just a power of the base. 2 is a power of 2, which is 1. So what we can do is go ahead and group these two terms together, and that's just a -1, so we're done with that one. So we have log base 2 of 70 minus log base 2 of 35, and then of course -1. What power of 2 equals 2? 1, the first power. So what's a logarithm? Power of the base. Now we're thinking, okay, well, this is a difference of logs, which we could write as the log of a quotient. And we've got the numerator here and the denominator here. So this will be log base 2 of 70 divided by 35. Now, when you look at this and you think, okay, well, what's interesting about this particular example is that, again, we have something very simple here that we can actually evaluate. That is now log base 2, 70 divided by 35. Well, that's just 2. So we have log base 2 of 2 minus 1. But of course, the base 2 logarithm of 2 is 1, so we get 1 minus 1, or 0. Now you can vary this. You can vary the argument here, make it maybe a power of 2 like 4. You could make a 16 or an 8 or whatever and get a different answer. But I just wanted to make a simple problem here where we get a very simple answer. The answer is 0. So again, when you are asked to evaluate based on the fact that you have the particular identities for the logarithm. Unless we solve like in the section on equations, WebAssign will ask for an exact answer, then it'll say approximate it, which will give you good practice using your Google calculator. So it's great to be able to approximate things, but if we've got a nice exact answer, we get a really great approximation because there's no round off error. Now, let's look at a couple of examples where we just use the laws of logarithms. So for instance, say we have something like this. And this is a WebAssign problem. It says expand. We don't expand as much in calculus, but let's just practice. We like to combine. Combining is the best way. Well, we expand sometimes in calculus to calculate derivatives, but in this class we'll be combining more. So we just have to take the context that we get. So we have the natural log of r divided by 8s. And what we want to do is just expand it. So that means we want to write this as some difference of logarithms where everything has been reduced as much as we can. So in this case, we have the log of a quotient, so we can say the log of a difference. So just like in the last problem, going backwards, log of r minus natural log of 8 times s. And then of course, this is fixed. We can't do anything here, but now we have the log of a product, which can be written as the sum of logs. So we have log r minus, now we'll use parentheses, natural log of 8 plus natural log of 7, using the product rule. And now when we distribute, always remember that we're going to have to distribute negative signs, so use your parentheses. So this will be natural log of r minus natural log of 8 minus natural log of s. Now, again, this is not a nice number. This is the power of e that equals 8. That's not a pretty number, so we leave it alone. This is an exact answer. And be sure when you have your s's that you make them look like s's. I will always write my 5s that have corners. 5s look like this, and s's look like that. So I know sometimes we get sloppy and our 5s look like s's, but be careful with that. Be very careful that you read the 5s and the S's correctly. Again, just formatting. So another thing we might want to do, say for instance, if we're in a calculus class and we need to take the derivative of a logarithmic expression, it would be easier to differentiate something in this form as opposed to this. So this would be something that we would do in calculus. Now in this class, what we're more interested in is combining or compressing. So this problem says combine. So for instance, we have 2 natural log 2. No preference for the natural log. It just is what Professor Ron wrote. You can use any base you like, but I want you to get used to this notation. So we have 2 log 2 plus 5 log x, where the log here is the natural log, and then we have 1/2 natural log x plus 7. So basically, we're taking this problem and going to the one object. So several objects combined into one object. So when we actually move in the reverse direction, we get one logarithm. And so when we're solving equations, the combination exercise is going to be something we're going to be interested in, because we can't apply the definition of logarithm if we've got several log terms. We just have to have one. So this will be something we'll do often in this class. And you did obviously in your college algebra class. So first thing, we're going to move all the powers up to these powers of the arguments. That is, this coefficient becomes a power. This coefficient becomes a power. This coefficient becomes a power. And you can move the negative if you want. It doesn't matter, your choice. So we have natural log of 2 to the 2 plus natural log x to the 5th. Again, the 5 becomes the power. Now we can just do plus natural log x plus 7 to the negative 1/2, just to mix it up a little bit. Students say, well, do I move the 1/2 and the minus, or can I just move the 1/2 and leave the minus out front? Either way, it will not matter. Does not matter at all. And if it did, this wouldn't be worth anything. The consistency is what we need in mathematics. Our theorems and our identities, etc., must be consistent. They must work together. So now we're thinking, okay, well, this is good. These are just a bunch of products. So first, I can put these two together. So I'll just use associative law, and then I'll rewrite this one to get rid of the negative power. So by the associative law, I've got the sum of 2 logs, which I can write as the log of a product. So I have natural log of 2 squared times x to the 5th. And that's a product. Then now, if you like, I can go ahead and write the x plus 7 to the negative 1/2 is 1 over the square root of x plus 7. Just to practice some with the exponent rules that we know very well from the previous part of our course. And now, again, you could have combined these two. It would not have mattered. And now we have the sum again, which we can put together as a single log of a product. So now we have log, and we just say this times this, but this will just move into the numerator and the denominator is there. So we have 2 squared x to the 5th divided by the square root of x plus 7. So now when you look at something like this, and then you're thinking, well, Professor Ron, 2 squared is 4, so let's just go ahead and write that as a 4. As long as it's an exact answer, WebAssign not going to quibble. They will always give you formatting directions, but if there are no formatting directions and what you've typed is an exact answer, then they won't quibble. I was talking to a student where we were coming up with a polynomial with certain characteristics, and WebAssign did not say to write in descending order. So I said, well, we can multiply all this out and write in descending order, but WebAssign didn't tell us that we had to do that. So I asked the student, I said, just write this as the product of these two quadratics, and it took it. So again, an equivalent answer is a correct answer, as long as it does not violate any formatting issues. If you have a formatting direction, then you must follow it. But WebAssign didn't say how they wanted us to write the polynomial. As long as it was an integer polynomial, it's like if you write 2 times 2 and the answer is 4, WebAssign will give you a green check. There's no reason for it to mark that incorrect. But if there is a formatting direction, you must follow it. So again, that's part of being a math student and part of being a future STEM professional. So being able to combine logarithmic functions or expand them will be things that we will do in this class, obviously, and then also techniques that you will utilize in calculus when you least expect it. You'll see it in Cal 1, you'll see it in Cal 2, and you will see it in Calculus 3. So these particular techniques will be useful. Now, what I want to do is just look at a simple example. I've shown you how you can change the base theoretically, but let's just say that we want to approximate a logarithm. And this is what WebAssign says, to 6 decimals. So you're thinking, okay, so you're going to give me a base that maybe I don't normally use. Like if I'm going to use my Google calculator, it might be a base that's not on the Google calculator, and maybe it's not a pretty number. So for instance, here's an example. Log base 2 of 540. Now, if Professor Ron uses his Google calculator, then I will need to use either what? Base E or base 10, because those are the 2 bases on the Google calculator. So that's what I can do. But first, let me just do a little bit of side calculation here. Notice, and this is not anything that difficult. For instance, we work a lot with powers of 2. 2 to the 10th power is just 32 times 32. 2 to the 5th times, 2 to the 5th times 2 to the 5th, or 32 times 32. And that's a very popular number. That's 1,024. And if we bump that down 1, that is, if we divide this by 2, 2 to the 9th, so that's going to be 5, 1, 2. 2 to the 9th is 512. Powers of 2 are so easy. We wish maybe we had base 2 arithmetic. Well, we do in computer science. So all you computer professionals will agree with that. So now what we're saying here is that this would imply that if we have 2 to the 9th as a lower bound for 540, and 2 to the 10th as an upper bound, equivalently, this would say we can just apply the base 2 logarithm because it's an increasing function. We'll use that often in this class, and you'll use it in calculus once you prove theoretically that the log function is increasing. We'll get log base 2 of 540 is actually between 9 and 10. And we would expect that it would be a little bit closer to 9, but again, the logarithmic scale is interesting. So this would say if we change the base and then used our Google calculator to approximate, we would expect to obey this inequality. And if we didn't get this, then we would check our work. Maybe we have a typo, maybe something's not working well. So now here's what we can do. You can use base 10 or you can use base E. Let's use base 10 because we know that's on the Google calculator. So log, base 10 log of 540 divided by log of 2. Now, when you use your Google calculator, let me go to that. And let's see here. Let me go over here and pull it up. Let's see, let me get rid of that and move this down. So I've got to get rid of all this extra stuff here because the Zoom doesn't like all this extra stuff. And let me get my Google calculator and let me move it here. Okay, and I'll get rid of that. Okay, so now let's go here. So here's my Google calculator. Again, it's free. Free is good. Free is not always that dependable, but this one is. So now here we've got log of 540, and then divide by log of 2. And this will give us, and we want to round this to 6 decimals. So we've got 9,076, 8156, or 81559 forever. So I'm going to mark off the 6. So that the 6 will round, the 6 decimal will round to a 6 to give us 9.076816. So this is what I'm talking about with your Google calculator. WebAssign will say, like when you solve your equations, it will say, give me an exact answer and then approximate. And this is good practice, so you can realize that change of base is quite remarkable. It does not matter which base you use. I mean, the problem may require that you use a particular base, but when you're asked to compute the base 2 logarithm of 540, that's a calculus problem that requires an infinite series, and that's what your calculator is doing. The idea is that you will use a base. For instance, if you had a table of logarithms and you just had base 10, you'd obviously have to use base 10. Or if you had a calculator that had base 10 or the natural base, you could use those. So the key here is that we are not required to use a particular base, but in a particular problem, solving an equation, we may need to use maybe base 2 or base 3 to move the problem forward. So when you have to actually approximate the logarithm of an argument for a base that you don't have access to, then you basically choose the base that where you have access. Either you have a table or you have a calculator that has the base 10 log or the natural log. So again, the main thing that we want to be able to do here is to note that theoretically, like I said before, problems involving logarithms can be adjusted to what we need. Problems involving logarithms here can be adjusted to recognize what we have access to. So that's very important. Now, there'll be some examples in your WebAssign where you can actually apply the laws of logarithms to do some interesting problems. So I want you to enjoy those. Again, the WebAssign basically walks you through steps and says, okay, now here's the next step. Apply what you know about logarithms. And I think they will be very helpful. That's where the WebAssign is very powerful. Now, the next thing that we want to do is to maybe consider situations where, you know, we think, well, we're in an algebra, if you're in an algebra class or a pre-calculus class, you're thinking, man, we solve equations. We manipulate functions. We use algebraic transformations. We do all kinds of things to really solve equations, because when we're doing calculus, we're taking derivatives to find horizontal tangents. When we do integration problems, we're solving problems where we're doing arithmetic calculations with a Riemann integral. So we're always solving for something, okay? So let's look at some examples where we actually solve equations that include logarithms and exponents. So here we go. Let's look. We're going to do several examples of these to get our feet wet. So we'll start out simple and we'll build. So we'll have the base 10 logarithm of 3 plus the base 10 logarithm of x minus 4 equals the base 10 logarithm of x. And what we want to do, and again, ladies and gentlemen, remember we had imaginary zeros with the polynomials. If we had real polynomials, we could end up with imaginary zeros, and they had to occur in pairs. When we solve these problems, we will be interested in real solutions. So we want to solve in R. With polynomials, we get a little bit of everything. And of course, imaginary solutions aren't going to be very useful in the calculus sequence, but when you take complex variables or complex analysis at the university as a future math major or engineer, you will definitely get back to the imaginary numbers. So in this case, we want to basically solve in R or solve for X. So one thing we have to highlight here are two extremely important properties. We'll just say this: base A exponential is 1 to 1. Base A exponential function, we've already talked about this, base A exponential function is 1 to 1. The base A logarithmic function is 1 to 1. Well, of course it is. If a function is invertible, its inverse is invertible, and that necessarily means they're 1 to 1. So the idea here is that you're thinking, what if we end up with a logarithm equals a logarithm? That would say if we had something like a to the x equals a to the y, then this would imply that x equals y. Likewise, the base A logarithm of x, equals the base A logarithm of y, would imply that x equals y, where these can be algebraic expressions. So the 1-to-1 property is what we would use to show that the function had that property. That is, this is the definition of 1-to-1. Now, there are other ways to prove that functions are 1-to-1, and we will learn about that in calculus. But for now, we want to use this. So we don't want to necessarily combine logarithms if we have a logarithm that equals another logarithm, as long as the bases are the same. That's really important. Different bases, we have to change the base then. So now, notice we can combine bases. We have the sum of logs. So log of 3 times x minus 4 equals log of x. Now, I want you to get used to this. When there's no base, ladies and gentlemen, we assume that the base is 10. This is the standard formulation for the common logarithm. And of course, for the base e, we use ln. That's a little bit easier to spot. But just remember, when you have no subscript in this class and mostly in our calculus sequences, the log will imply or mean base 10. So now notice we have 1-to-1. We have a logarithm equals a logarithm. Of course, we could subtract the logs and do a quotient and that, do all of that, but that's more work than we want to do. We'll just go ahead and use 1-to-1. So this will be implying the following: 3 times x minus 4 equals x. So the idea here is that if we have a 1-to-1 relationship, we can now set the arguments equal. So this will be 3x minus 12 equals x. And then, of course, we can subtract x from both sides. We get 2x and add 12 to both sides. divide by 2, and x is equal to 6. Now, this is a value of x, and then when we look at the original equation, we see that 6 makes sense here. That is, we know that the argument of the logarithm, if we take the logarithm of an argument, that argument must have a positive value. It must have a positive value. And so, of course, 6 minus 4 is 2. That makes sense. And of course, log of 6 makes sense. So this is a good value. And so we can write solution set real number 6. So again, when you get the equivalence of 2 logarithms, just like you have the equivalence of 2 exponentials of the same base, you can use the one-to-one property. And that's a big time saver. So think about it. If the bases aren't the same, you can change the bases. And once the bases are the same, you can set either the powers or the arguments equal and move the problem forward. And that can mean anything depending on how complicated the arguments are. So let's look at the next one. We have several examples. We're going to spend most of the class doing these. So we have 3 to the 5x minus 1 equals 4. Now, this is where I wanted to give you some practice using change of base, and then also letting you know that the power rule is flexible for any base. Now, notice here, you're thinking, well, we have many ways to do this problem. We could change the base, that is, we could change this 4 to a base 3 exponential, but most of you would frown at that and say, Professor Ron, I don't want to do that. And later on, I'll show you how to do it. So, but I want to give you a simpler method here. Now, we can look at this and say, well, the power of 3 that equals, in this case, 4 is 5x minus 1. Let's say that again. The power of 3 that equals 4 is 5x minus 1. 5x minus 1 is a power of the base. It's a logarithm. So the first thing you can say is 5x minus 1 equals the base 3 logarithm of 4. That's just the standard exponential form of this, logarithmic form of this exponential form. What's a logarithm? The power of the base. So 5x minus 1 is indeed a logarithm. That it is the base 3 logarithm of 4. And then you're thinking, okay, well, I can solve for x, so let's do it. So now we have 5x equals the base 3 logarithm of 4 plus 1. And so x equals 1/5, that is, we divide by 5, base 3 logarithm of 4 plus a 1. And that would be an exact answer. And of course, the exponentials are very flexible here. You know, you can put any real number in here, no limitations. And so this would be an adequate representation of the solution. Now, one thing you might think is that, okay, well, I see what you did, Professor Ron. You just used the logarithmic form of the exponential form. Now, of course, another way would say, well, just use your favorite logarithm base and like take natural logs. You get the same answer, but in effect, you'll be changing the base. So, for instance, if you did that and used the power rule, you'd still get an equivalent answer, though it wouldn't look the same. Now, here's the thing. Say you're working this problem and WebAssign says, can you give me an approximation? And then you're thinking, well, you know, I don't have base 3 on my calculator, so we could change the base. We could say, okay, well, x will equal 1/5. And then we can just maybe go to natural log. So we'll do natural log of 4 divided by natural log of 3. That is ln of 4 divided by ln of the old base, so to speak, plus 1. And that would be an equivalent answer. And so that would be useful to us, and that would have been the answer had you just taken natural logs. But I want you to be adept at going from the exponential form to the logarithmic form, always, because that is the definition of the logarithm. What is a logarithm? A logarithm is a power of the base. Unfortunately, when you start calculus, you'll define the natural logarithm by an integral, and that will not look anything like what we're doing here until you work with it for a while, and then you'll say, you breathe a sigh of relief and said, oh, thank goodness everything we learned in pre-cal was actually correct. So the idea here is we have a solution, and then you can say, okay, well, let's just put this in a solution set. We'll go ahead and put this one in. We'll put one of the forms. There. So again, when it comes to solving logarithmic equations or exponential equations, you have plenty of flexibility. That is, you don't have to worry that your technique may be different from your classmates. As long as you and your classmate are applying good mathematics, the responses that you glean will be equivalent. Again, everything has to be equivalent. So I don't really worry. WebAssign doesn't really care if they ask for an exact response. If you type it in base 3 or base E, the WebAssign is fine with that. They use the MATLAB backbone to check the computer, your algebra. So that's why the WebAssign is so sophisticated. It has very, very sophisticated computer logic going on. The code is voluminous. It's like the code you would use for Maple or Mathematica. Now, let's look at another example. You know, Professor Ron likes the quadratic form. We live for quadratic form. Why is quadratic form good to us? Because we understand the quadratic equation. And if it's quadratic form, we can solve it. So let's look at this one. This is 3 to the 4x minus 3 to the 2x minus 6 equals 0. So when you look at this, you're thinking, okay, well, we want to solve in R. So again, solve in R. And you look at this and say, okay, well, this is quadratic. We've got a constant term here. Here's our non-squared term. And of course, if we square this term, we get a 3 to the 2x. So we've got coefficients that we would have in a quadratic equation. So let's dress it up a little bit. So we have 3 to the 2x squared. And of course, this one will even factor. So this is lucky. And then we have minus 3 to the 2x. So I'm using parentheses so you can easily see here's the non-squared term and here's the squared term. And then we have the constant term. So we say this is quadratic. And this occurs a lot in calculus. Quadratic in 3 to the 2x. So this is a quadratic equation. And so we can think, can we use Professor Ron's AC lemma? I think you can see that we can, because here we have a 1. So AC is just 1 times -6, or just -6. And we just need a -1 here. We got, well, you can just like -1, just like do a little 1 there and a 1 there. A times the squared term, B times the squared term, and then the C, the constant term. And so you say, okay, well, we'll just use what? -3 times 2. That'll give us the -1 when we add these. So now we can factor this. So this will be 3 to the 2x minus 3. Oh, how interesting. That's an exponential equation. And then we have 3 to the 2x plus 2. So again, with the AC method, we didn't have to use the quadratic formula, which really makes the problem a lot easier. And then we say, oh, okay, so there's a -6. There's the 2 times the 3 to the 2x, and there's the -3. That gives us -1 copies. And then when we square it, we get to the 3 to the 2x squared, 1 copy of that. So this works. And so now we have the zero product. So that means we set each of the factors to 0. So this will mean that 3 to the 2x equals 3. That is, when we set this equal to 0, 3 to the 2x equals 3, or 3 to the 2x equals -2. So if this equals 0, then we move the 3 over and get 3 to the 2x equal 3. If this factor equals 0, we move the 2 over, excuse me. I left out my equal sign. We definitely need that. Again, the mathematics is always tells us exactly what we need to do. And so now we're thinking, well, you know, Professor Ron, you said we need real solutions and the exponential functions are positive. So this would not have a real solution. So we'll just say no real solution. When you do complex analysis, there'll be more stuff to do, but a real exponential is never less than 0. So that doesn't give us anything. We're done with that. But that's just a 1 right there. Okay, so you're thinking, you know, this is what, go back up here. This is exponential 1 to 1. That's why I kind of giggled when I saw this. I'm thinking that makes a good example of what we were doing earlier, but a much simpler example. So now we got the bases the same. So this would be equivalent to 2x equals 1. So x equals 1/2. So we don't have to do any difficult work here. We just got powers of the base, so we set the powers equal. And so in this case, we have 1/2. And so nothing there, but the 1/2 clearly works. And that would be our solution. So when you think about what we're doing with logarithms, we look at this and say, okay, we get to use all kinds of relationships. We get to use the identities here to combine logarithms. We get to use the definition of the logarithm. And here we just get to use the quadratic form. And then use what we know about exponential functions. So it all ties together. Now, let's look at some examples that, for instance, we're pretty good at looking at combining logarithms. And we're pretty good at recognizing the quadratic form. And then, of course, if we need to write in an equivalent logarithmic or exponential form. Let's look at an example. And this is where we'll get to use our Google calculator because the numbers get kind of large. This is an interesting example. We have log base 2 of log base 3 of x equals 4. Now, again, when you look at something like this, you're thinking, oh, okay, well, I've got the logarithm of a logarithm. So what's a logarithm? It's a power of the base. So when we look at this, we see the power of 2, in this particular case, that equals the base 3 logarithm of x is 4. That's what a logarithm is. So we go to the exponential form. Again, what's a logarithm? Power of the base. The power of 2 that equals base 3 logarithm of x is 4. So this says 2 to the 4 equals base 3 logarithm of x. Or equivalently, we have base 3 logarithm of x equals 16. So just in looking at this, again, we have to know what a logarithm is. A logarithm is a power of the base, but the argument of the logarithm function is a logarithm. So we have another logarithm. Okay, well, let's do the same thing again. What's a logarithm? It's the power of the base. So the power of 3 that equals x, x here is 16. That's a big number. So now we have x equals 3 to the 16. Now, when I was looking at your WebAssign, it doesn't want you to enter a an exponential number, which of course would be an exact answer. So then we have to say, well, what does this equal? Well, this is just what, 3 to the 4th. Well, let's write this in a way that would actually be simple to write. For instance, we can say 3 to the 4th to the 4th. That is 4 times 4 is 16. So this would just be 81. 3 to the 4th is 81 to the 4th. So that's 81 times itself 4 times. So that would be formidable just to write down. So for instance, if you wanted to do this, and you could do it, you could say, well, this would equal 80 plus 1 squared times 80 plus 1 squared. Now I did some calculations here, and when you do 80 plus 1 squared, so what does this equal? So let's do some side calculations. 80 plus 1 squared, that's just the binomial. So that'll be 80 times 80, which is 6,400. And then we have 1 times 80, which is 80, times 2, which is 160, plus a 1. So this is 6,400 plus 161. So that gives us a 1, a 6, a 5, and a 6. 6,561. So now this says equivalently 3 to the 16 is just 6,561 times 6,561. Now, at this point, you're thinking, okay, Professor Ron, I've had enough of your arithmetic here. So here's what we can do. We can go to our Google and clear this out and say 6,561 and square it out. And we get 4,304,000, or actually 43,046,721. How interesting. So this will be 4304671. That's a big number in this case. So basically, let's see 1, 2, 3, 1, 2, 3. Do I have enough zeros here? 4304671. So 1, 2, 3, 1, 2, 3. Yes, that's 43,046,721. So once you get to this point, and this is why I went ahead and did it this way, ladies and gentlemen, you can multiply this out and get these numbers. But WebAssign doesn't want this. If they will allow you to type an exponential number, then the palette will come out. But if it doesn't, you've got to type an exact number. So now we see our solution set is 43,046,721. How fascinating. So it's all good. Now, one thing that we can do now is we can actually do some word problems that actually utilize some of our new ideas. So let's do that. So think about this problem as being a good culture problem, where we basically dissect the definition of what? Logarithm. What's a logarithm? Power of the base. You should put that on a note card, and then when you wake up in the morning, you read it and say, a logarithm is the power of the base, and we'll get where we need to go. Now, what I want to do, we've done some problems with some logistic growth, and we've done some problems with the interest. So I want to do a couple of examples where we get to use some of these and use our newfound techniques. So here's an example. And then, of course, if WebAssign wants an approximation, we'll give it to them. So here's what we want to do. We want to invest $5,000 at 8.5% compounded quarterly. So this is something like we did last time, but it's going to have a few new twists to it. And then what we want, A, is compute the amount in 3 years. That's easy. We know how to do that. Compute the amount. Compute the amount in 3 years. And then second part, B, says compute the time to triple the investment. Compute the time to triple the investment. Well, let me write the B. To triple the investment. Okay, so we look at this and say, well, let's just say 8.5, 8.5%. That'll be a 17 over 2%. So that's just what, 17 over 200. If we write that as a fraction. And so now for A, this is reviewed, but it's always good to do this. This A will be 5,000. And then we have 1, and this is quarterly, right? So N equals 4 for quarterly. And we have a T equals 3. So now we have 1 plus 17 divided by 200 divided by the N, which gives us, well, we know what the N is because I wrote it down. That's equal to 4. And now we have the NT, so 4 times 3, which is 12. So I'll just write 4 times 3 so you can remember the formula. So this will be 5,000. Now, of course, the 200 times the 4, that'll be 800. A lot of you will send me messages where you're not getting good rounding. It's because you're rounding and not doing it like I'm teaching you. Do an exact calculation. If you round in the calculation and then you keep getting the answer marked wrong, it's because you're not doing what I'm asking you to do. So do an exact calculation until you approximate. That way you don't have to worry. And then this will get, well, we can add, so we've got what, 800 plus 17, so 5,817 over 800. So when we get the common denominator, we have 800 plus 17, which gives us that number. And then we raise that to the 12th power. Now, this is exact. This is where I've already shown you how to use the Google calculator. This requires calculus, an infinite series, the binomial theorem. And so when I use my Google calculator, I got 6,435, and I just ran it out to several decimals, 0.931. So WebAssign said round to the nearest cent. So this will give us $6,435.09. Okay, that's just review there. But I wanted to do this so we could set up for the next problem. Now it says compute the time to triple the investment. Well, the part right here, the 1 plus the N over R, that's the same for all of this. So we've already computed that part. So for B, triple the investment is just 3. Let's just write this 3P. So if we say P is equal to 5,000, we can just use symbolic computation. We have 3P equals P And this part we already know. That is, we have the 1 plus the n over r, which is 817 divided by 800. And now we have 4, which is the n, but the t we don't know, so we have 4t. So basically, we have to solve for t. So again, we know that the n is fixed. We know that the 1 plus n over r, that's the fixed base of our exponential function. This is an exponential function, just the base looks kind of odd to us. And then we need to solve for t, because we need to know how long it's going to take under these circumstances for this money to triple. That is, become 15,000. So now we can see that the p is absorbed. And this will give us, let's just write this on the left-hand side, 817 over 800 raised to the 4t equals 3. So now you're looking at this and say, well, Professor Ron, I don't want to use base 817 divided by 800. And I don't blame you. That's a little bit ridiculous. So what I will say here, when the bases get kind of strange, so I'm gonna say use a logarithm that you like. So at this point, use, and I've written here in my notes, use natural logarithms, or you can use base 10 logarithms. Use natural logarithms. So again, sure, you can use this base, but that's not required. So now we can use natural logarithms. So this will be, bring the 4t down, take the natural log. So this will be 4t by the power rule, natural log of 817 divided by 800 equals the natural log of 3. So again, when we take the natural log, the 4t, which is the power, becomes a factor. So we have 4t times the natural log of 817 divided by 800 equals the natural log of 3. And so now the t, we just divide by 4 times the natural log and leave the t over here. So if and only if t equals natural log of 3 divided by 4 times the natural log of 817 over 800. And that's the exact time, ladies and gentlemen. That's the exact time for the tripling time. So what we can do at this point, and like I say, you can use the base 10 log if you want. We'll go to our Google, and we'll just say natural log, so ln. The Google calculator is easy. You can use it on your quizzes and things. It makes it real easy. It's right and convenient on your computer. Dividing, and then we'll use parentheses, and we'll say 4 times, and we'll use natural log, and we'll have 817 divided by 800. Again, we need a nice calculus approximation here because we want our clients to be happy and close. And this will give us approximately 13.06169. And WebAssign says round to 2 decimals. So this will be 13.06 years. So again, if you watch my Smart Pen videos, even though we have the lecture, the idea is that we always look for an exact calculation. A lot of your friends might be business majors. I used to teach a lot of finite math. Finite math is kind of fun because, again, the students would always suffer from round-off error, and I have to tell them, I said, we've got to have an exact calculation, and then the exact calculation will allow us to write the answer cleanly. And then we can go to our approximation device that will use the infinite series, use the calculus to give us a nice decimal. So our friendly calculators do us a lot of good. And we are grateful to have the computing devices. Again, the goal should be this. And then we use our computing device to give a nice approximation of this so we can keep our clients happy. Now, of course, as you do other examples, you will utilize formulas just like this and use your new techniques for solving to get a nice approximation. Now, what I want to do are some additional problems, solving equations. Now, one thing that happens often, and again, when we look at problems involving applications, just like with the last example, we want to make sure that our computations are clean, that our computations move us to an exact response so that we don't have to worry about any errors that we may have introduced due to negligent rounding or poor mathematics. So what I want to do now is to look at an inequality. And you're thinking, well, we've done a lot of inequalities, Professor Ron, but now we're going to look at one with some exponentials. So we have x squared times e to the x minus 3 times e to the x. And this is going to be less than 0. So when you look at this example, the first thing you think about is, you know, we have a BV technique and we want to see if we have any zeros over here. Clearly, it's never going to be undefined. The exponential is defined for all real numbers, and x squared, no problem there. So the first thing we look to see, well, we have a 0, and then we can factor the left-hand side. So let's factor this and see what we get. So we have e to the x times x squared minus 3 is less than 0. Now, again, some of you are afraid of complete factorization. Complete factorization means factor completely, okay? When you all send me messages and you got quadratics in your polynomial factorization, you have not factored completely. And I'm not really sure where the disconnect is, because you know I'm big on the complete factorization, because at this point, even though these are real zeros, this is not completely factored. This is a difference of 2 squares. So we go ahead and finish the factoring process. So we have e to the x minus square root 3 times x plus square root 3. Now, of course, when we're doing this in a formal manner, we would say x minus the negative of square root 3. So we see what the 0 is, but we get away with the plus. We see now here that we have 2 zeros that are distinct, the square root of 3 and the additive inverse of the square root of 3. So again, complete factorization gives us this. Now we have to say, okay, well, we can finish now. The factor e to the x, as we now know, is never 0. It's always positive. So we just observe that e to the x is always positive. So this will not give us any BVs, but clearly we have the square root of 3 and the negative of the square root of 3. So we've got BVs, square root 3, and the negative or the additive inverse. But this is an easy one because these are just multiplicity 1. Remember, multiplicities are important too. When you talk about a polynomial of degree 4, it's going to have 4 zeros. It could have all zeros are the same. 2 are the same, pairs, whatever. You can have all kinds of combinations, but you must count multiplicities, which I've said many times. So now we'll have negative square root 3, and we'll have square root 3. Now, of course, we can do our multiplicity bit, but if you want to check like a negative 10 just to see what's going on here, again, this is always positive. So if we substitute the negative 10 here, we get negative, and of course negative 10 here we get negative. So this is the positive. So we're above, and then we have to cross. And then the multiplicity says we have to cross again. So again, you can go ahead and check all of the factors here as I do in the videos, but I try to introduce some techniques that may make your work a little bit quicker when you're working on a test, so you can move through the problems quicker. And so now we have negative here, and again, we have positive here, but we've got strict, right? So this will be a check here, but these both get X's because they actually make the left-hand side 0. So when you're working the inequality here, you work it just like we did before. We just now have a new object here that really doesn't make any difficulty at all. If anything, it makes the problem easier. So now this implies that X will live between these two real numbers. So we have negative root 3 to positive root 3 with the parentheses. So again, when it comes to inequalities, we're not doing anything new in the sense that we're still doing the same type of computation. What we want to be able to do is, if necessary, introduce some new functions. And again, don't look at the new functions as changing the technique, just look at them as new objects, which will require maybe a little bit different analysis. Again, we go to the fact that when we started our analysis here, even though it's been limited, the perception, at least intuitively, is that this is a positive output function. Now, here's an interesting example from your WebAssign that I want to do. We've got some equations here of interest. Now, what I want to do first is going to use a change of base. So we haven't used the change of base in a theoretical sense of solving an equation. So here's an example that says, okay, I showed you how to change the base if you're just trying to do an approximation, but maybe you're trying to solve an actual equation where the base has to be a particular one, and you don't have much of a choice if you want to move the problem forward. So here's an example. We have log base 3 of x plus, and you can make these problems up. You can make up all kinds of fun problems with logarithms as you get more and more used to these, you know, getting the rust off from college algebra. Base 9 log of x plus, and of course you can make them up to look just like this or change to different powers. Base 27 log of x equals 11. So again, we want to solve in R. So when you look at this, you're thinking, okay, well, I can't really combine these logarithms with the identities because the bases aren't the same. And so you're thinking, well, this is not too bad because this base is a power of 3 and this base is a power of 3. So intuition would say, let's just make everything into 3. That's a 3. So let's make that into a 3 and make this into a 3 since we have convenient powers. But even if we didn't have convenient powers, it wouldn't matter. We need one base. And so since we're kind of lazy, we're thinking, let's just go the lazy route. And so the first thing we would do is convert all logs where it's necessary to base 3. Now, techniques of computing are not unique. I'm just giving you something that will be easy to do. So now equivalently, log base 3 of x plus, okay, now we just do the cosmetic change. We change to base 3 like we would like math to be, just change it up and we're done, but we know that's not true. Then we have base 3 log of 9. So we take the new base log of the old plus log base 3 of x, and then we divide by the base 3 logarithm, the new base of the old. So the idea here is that this is just change a base formula that we reviewed at the very beginning of the class and we proved, which was not difficult at all. I mean, let's think about it. We often have to decide how we're going to move forward with the proof, but it was very easy, just 2 steps. So now we have log base 3 x, and of course, the base 3 logarithm of 9 is 2. What power of 3 equals 9? It's 2. So we get log base 3 of x divided by 2. So now you see why I chose to move to base 3, because we have such simple numbers. And then, of course, what power of 3 equals 27? Well, 3. What's the logarithm? Power of the base. So now you can see that we just have one logarithm, one base, and we can factor. So base 3 logarithm of x is common to all of these terms. So we have 1 plus 1/2 plus 1/3 equals 11. Now, when you look at this and you think about this, you're seeing, okay, this was not a bad way to go because the numbers aren't so difficult. And now we're just going to end up with a logarithm equation with one logarithm, and we know how to do that. So let's go ahead and simplify. So we have log base 3 logarithm of x times, again, I've got the base 3 logarithm here to the left, and this is just the coefficient because I've written it on this side. You can put it over here if you want. This is not part of the argument, but we need a common denominator. So 2 times 3 is 6. Oh, how we would like easy denominators when we were doing our time, rate, distance problems. So now let me move my cursor over here. So this is going to give us a 6, and then a 2 into 6 will give us a 3, and then a 3 into 6 will give us a 2. So now we've got what? 5 plus 6, that's 11. So we have 11. I'll go ahead and write this out to the left. 11 over 6 times the base 3 logarithm of x equals 11. Well, that was convenient. The 11's absorbed. So we have the base 3 logarithm of x cross multiply by 6 equals 6. So looking at this and looking at this, we opt for this because this is trivial, I mean, compared to this. So we see that the utilization of the change of base theorem allows us to do what we do in mathematics. What do we do in math? What do we do? We take the problem and we simplify it. When you solve an equation, you simplify the equation to a form that reveals the solution. We have done that from day one. You have done that from day one in your math classes, and nothing of anything has changed. The technique is always the same. We simply learn to deal with new objects, and the problems get more complicated, but we're still simplifying things. So now we say, well, what's a logarithm? It's the power of the base. The power of 3 that equals x is 6. So x equals 3 to the 6. We can't get away from these powers of 3, but at least this is reasonable. So this is going to be what? 9 times 9 times 9. That's reasonable. Much more so than the 43,046,000, whatever we had, 421, I don't know, big number. So we got 81 times 9. So that'll be a 9 and a 72. So now we see that if the base 3 logarithm of x plus the base 9 logarithm of x plus the base 27 logarithm of x equals 11, then you might think, well, you could sit here and play with the numbers and maybe come up with this. But at least arithmetically, from a standpoint of logarithm theory, we get 729. So the answer is 729. Now, I will say this. It's always nice to be able to intuit answers, but when the answers are unfortunate and not beautiful numbers like 729, then you don't have that luxury. So the technique here is very important. Now, let's do the same. Let's do the same kind of problem with an exponential. And maybe we'll just convert it to a quadratic. So we want to take the same approach, but instead of logarithms, let's work with exponentials. So we have 4 to the x minus 2 times x plus 1. So these are exponential functions, equals 3. And we want to solve in the real numbers. So again, if we've got extra log terms, we want to combine them like we did on the last problem by making sure all the bases were the same, or maybe we have all the bases the same and we want to combine with the quotient rule or a product rule. That is a luxury that allows us to solve these types of equations. But now we look at this and say, well, we're not quite there yet. We know that this is 2 to the x times 2 if we use the laws of exponents. And this is actually the square of 2 to the x. So now we're thinking if we change the base here using the laws of exponents, then we will have quadratic form. So our intuition says, okay, let's do a little bit of work with this. 4 to the x is just 2 to the x quantity squared using the laws of exponents. And then we have minus 2 times 2 to the x. Because 2 to the x plus 1 is just 2 to the x times 2. So again, we have a squared 2 to the x. We have a first power of 2 to the x. And then if we bring the 3 over, we have a minus 3 equals 0. So this gives us a problem like we had before, but it wasn't written in a very convincing way. That is, we had what we needed, but we didn't have to do this much work to it. So now we can see when we look at this, we see again of a similar nature, quadratic in 2 to the x. So we've got what? We've got our 1, let's put the 1 there, the shadow 1. We have an a, the coefficient of the squared term is 1. The coefficient of the non-squared term is -2. And the coefficient here, the constant term is -3. But again, we can use AC. I mean, you know, the harder problem would be that we would have to what? We'd have to use the quadratic formula. So now AC will be 1 times -3 or just -3. When we need the 1, we use it often. I mean, it turns out to be very useful. So now I'm just going to go ahead and stick it in there. Now the 1 is actually useful because -3 plus 1 is -2. So that, boom, that works. So now we have 2 to the x minus 3 times 2 to the x plus 1 equals 0. Now, of course, when we look at this and we think about this kind of problem, it reminds us exactly of what we had before. So now, again, quadratic, these make good test questions. They actually aren't as difficult as some of the other problems we've done. And so now, when we look at this by the zero product, we see that 2x, or 2 to the x, equals 3. When we set this factor to 0. And then, of course, here, or 2 to the x, transposing the 1 equals -1. But again, we know that the exponential function has positive output. So here we have no real solution, just like we had before. So this factor would not give us any real contribution. But now here, again, you're thinking, well, Professor Ron, do we want to change the base, or are we just going to use the definition of logarithm? Let's just use the definition of logarithm, then I'll show you how to change the base on a problem where it would probably make more sense. So now we say, okay, well, the power of 2 that equals 3 is x. So x is a logarithm. It's a power of the base. So x equals the base 2 logarithm of 3. Now, this is a valid solution. But now, of course, if you are interested now, and of course, if you type this into WebAssign and use the log, the math palette with the subscript, with the base 2 log of 3, that would, of course, get you a green check. But if you were interested in using the Google calculator to get an approximation, maybe you want to change to base E. So we could just change to base E and get natural log of 3 divided by natural log of 2. So the idea here is both are equivalent, but this would allow you to get an approximation if WebAssign requested. So a lot of the problems in this section, in the 4.5, basically just say, okay, give the exact solution, and then please give an approximation of the solution, just to give you practice using your Google calculator. So now we're done with this. That is, we'll say the base 2 logarithm of 3. And then, of course, you could write it this way if you like. Again, WebAssign's not going to care. It doesn't matter. And don't worry. An exact answer is just that. If it's formatted correctly, you can use any base you like. You just have to be careful. And this is one thing that I want to emphasize, ladies and gentlemen. Check your work. And when you type something, you just don't hit enter. No. You don't. You go back through your work, and then you look at what you've typed, and you make sure it's exactly what you want. And if you're not sure, don't hit enter. Don't even submit it. Wait. Go back to it. The key to success is to not throw caution to the wind. You can't just think the computer's going to read your mind. So be very careful. And I know it is a learning curve. It is hard to keep focused. But again, be very careful that you make sure that your work supports good mathematics, because every step of the problem is important. We start here, important step, everything's important. There is no step that is unimportant. And if there's a kink, we have to find it. And unfortunately, we are human, and mathematics is that way. But that's what makes you good as a future STEM professional. You have a higher standard. You have a higher standard to obtain as a STEM student. It is difficult. And there are many people that want to travel down the STEM career path because the rewards are huge, but the price is exacting. You must work very hard. Now, what I promised here is, for instance, say we have a non-user-friendly exponential equation. So we have something like 3 to the x plus 2 is equal to 5 to the 2 minus 3x. Now remember, when you're doing difference quotients with exponentials, all of the stuff, so-called the x plus h, must go into the power. So be careful when you type these things that you're actually respecting the exponential function. That's very important. So now solve in R. When you look at this equation, you're thinking, well, Professor Ron, I want to use 1-to-1, but it's kind of like the problem we had with the 3 different bases, the 3, the 9, and the 27. We have a base 3 here and a base 5 here. And then you might be thinking, okay, well, I can't use 1-to-1 unless I change the base. So we might think, okay, well, we can change this to base 5, and then I'll have base 5 equals base 5 and set the powers equal. Or you're thinking, well, I could just take natural log of both sides and get my expression that way. No problem. But I want to give you an example here of changing the base. You can always take common logs or natural logs, but it is important to be able to change the base. So here's what we're going to do with this problem. But again, remember, you have complete flexibility. We'll say convert all terms to base 5. Now, of course, this is already base 5. So we'll use our base 5 exponential change of base, or just base A exponential change form. So we'll have 5, and this will be x plus 2 with the power rule, log base 5 of 3. So remember, we just do 5 to the log base 5 of 3 to the x plus 2, and then just move the x plus 2 down by the power rule. So again, when you change the base, it's really cosmetic for the exponential functions. There's no proof. It's just the definition of inverse functions. So that makes it a whole lot easier than the change of base for the logarithms. Even though they're essentially doing the same things, we found that the nature of the logarithm and the exponential require a little extra work, even though they're doing the same things. When we actually have to find that power, it's a little bit more difficult for us. So now, if we change base 3 to the x plus 2 to base 5, we get exactly this. And then we can set this equal to 5 to the 2 minus 3x. So this offers a technique that's actually quicker than taking natural logs. And then at the end, if you want to change the natural logs, you can to evaluate. But now when we look at this and we look at what's going on, we have the equality of 2 exponential functions of the same base. So now we use one-to-one property. So this would be equivalent to saying, now remember, this is a number. This is the power of 5 that equals 3. So we'll just call this x times the base 5 logarithm of 3 plus 2 times the base 5 logarithm of 3. That's just a number. What's a logarithm? Power of the base. And this equals 2 minus 3x. So we set the powers equal. And I just multiplied here, x times the base 5 logarithm of 3 plus 2 times the base 5 logarithm of 3. And now notice here, you know, don't think of this as anything but just a number. There are lots of letters here, but it's a number. So we want to get all the x's on one side. So let's transfer the negative 3x over to get the plus 3x. So we're going to get x times base 5 logarithm of 3 plus 3x. And this will equal, so we've got a 2, and now subtract the non-x term minus 2 base 5 logarithm of 3. And now, of course, we can solve for x. We just have an x that's common to both of these, so we'll factor the x from these two terms. So we have x base 5 logarithm of 3 plus 3. And if you like, I mean, maybe you want to go ahead and factor the 2. Go ahead and factor it. You know, Professor Ron factors everything to death anyway. It's okay. Factoring is a learned technique. And if you think you can get to calculus and not have to factor anymore, then you think incorrectly. The art of factorization is implicit in good math student strategy. It is a technique that is required and will tax you at times when you thought you knew how to factor. As you do more mathematics, your techniques of factorization will improve. They will of necessity have to improve. So now when we divide here, we've got a number times x. So we're going to divide both sides by that number. So we have 2 times 1 minus the base 5 logarithm of 3 divided by the base 5 logarithm of 3 plus 3. Now, what's interesting about this, again, we have these nice exponential functions, and the x's can be any real number. We're not worried about any problems with radicals or division by 0. So now, if you needed to convert these to base e or base 10 for computational purposes, you could. But now we have our solution, 2 times 1 minus the base 5 logarithm of 3 divided by the base 5 logarithm of 3 plus 3. So what we see is when we actually use the change of base, this allows us to use the one-to-one property for exponentials, just like we would use the one-to-one property for logarithms. The idea, ladies and gentlemen, is that you have, just like with all the problems we've done before, many techniques at your disposal. One technique is not necessarily better than another. It may be better for you because you have more facility with it. But when you type your solution into WebAssign, an exact solution is all WebAssign wants. And then you can use your Google calculator to get a decimal approximation if that's what WebAssign requires of you. And a thing, and I'm not bothered by that. I think that it's a good thing to actually be able to get that approximation, because again, as a future STEM professional, approximations can be very useful for your clients. You're working in a laboratory, or you're working in a computer lab, or you're working as a research mathematician or a mathematics professor training future STEM professionals. The idea is that approximation is good, but we want our approximations to be valid because we have good mathematics to support the effort of approximation. Now, the last thing I want to do, I don't know if we'll have time to finish, is I want to do a calculation to actually find a solution to an exponential equation that requires a quadratic technique. But the quadratic that we get won't have nice solutions. So we'll have to use the quadratic formula. So here's an example. When you take Calculus 1, you will actually, at the end of the course, study the hyperbolic functions, which will be very fascinating functions that mimic the standard trig functions. And here's what we have. We have y, this is actually the hyperbolic sign, e to the x minus e to the negative x divided by 2. Now, when we look at this, here's what I want you to do. I want you to solve. I thought I'd make up a nice question here. This is actually the hyperbolic sign. This formula is the hyperbolic sign. And I want you to solve y equals e. Now, I'm not asking you to solve something that has no solution. So I want you to find the value of x that actually will give you an output of the standard base e. That's the natural base right there. This is kind of an interesting problem. Natural base e. Okay, so if we do that equivalently, we just say e to the x minus e to the negative x divided by 2 equals e. So maybe you're doing a WebAssign problem and this is what they say solve. Maybe that's what you get. You don't even get all the pomp and circumstance here. You just get this. And you look at this and say, okay, well, interesting. So the first thing you're going to think, well, we want to cross multiply and get all the terms on one side. So let's do that. This is a standard technique in mathematics. I want you to know how to do it. So we get 2e, that is e to the x minus e to the negative x equals 2e. And then if you will, and let me touch up the focus a little bit cleaner. There we go, it looks a little better. Now we want to retire everything to the same side. So this will give us e to the x minus e to the negative x minus 2e equals 0. Now, when you look at this equation and you think, well, you know, Professor Ron, we've done equations that have quadratic form. And this is an opportunity for us to say, okay, if we multiply by an algebraic expression, we can actually find zeros. This will help us to find zeros. We may get additional zeros that are not solutions of the original equation, but it will uncover any solutions that are in the original equation if they exist. So here's what we're going to do. We're going to convert this to quadratic form. So what we're going to do is multiply by e to the x. This is a standard technique in analysis, and it's what we've done when we've done like a conjugate method or something. So here, we're going to transform this equation into a quadratic so we can analyze it and then see what it gives us. So multiply by e to the x. So this will be e to the 2x, and if you like, just do 2x. E to the x times e to the x is e to the 2x. And then here, we've got e, I'll write this out, e to the negative x times e to the x. That's just going to be a 1 with a minus, but I'll write that out. And then we've got minus 2e e to the x equals 0. So now we have a quadratic term, e to the 2x, that's the square of e to the x. And then we have this term, minus 2e times e to the x. And then, of course, e to the x times e to the negative x is 1, so we get minus a 1. So now what we see is this equation is quadratic in e to the x. So Weber sign could have been even better to you and started with this. So we say quadratic in e to the x. Now the thing about this, you see that e there and you're thinking this will not factor. No hope. AC method gives us a -1, and that's never going to give us that factor. So we look at the quadratic formula. So we have b squared minus 4ac. So we have negative 2e, that's the b squared, minus, and there's a 1 and a -1, 4 times 1, -1. So again here, we've got the 4e squared minus plus 4. So we can factor the 4. So remember, just like I've done before, if we know AC doesn't work, we go straight to the discriminant, which is part of the quadratic formula to figure out what kind of zeros we have. This is a positive number. So this is going to give us 2 zeros. Maybe one of them won't work. Maybe, hopefully, we'll keep our fingers crossed. Hopefully one of them does work. So now we put this into the quadratic formula. So we have x is the opposite of b, which will give us 2e, plus or minus the square root of this. Now the square root of 4 is 2, so that gives us 2 times the square root of e squared plus 1, divided by 2a. Again, we have a 1 here, so 2 times 1 is 2. Now, of course, the 2's absorb, and we get e plus or minus the square root of e squared plus 1. Now, this is where, and of course, let me put my e here. This is quadratic in e to the x, so I have e to the x equals it, not just x. I mean, that, just remember, quadratic in e to the x, and so we have to be vigilant. So this is e to the x. Again, the math will not let you write something incorrectly for too long. It'll eventually kind of say, all right, wait a minute, why are you changing the mathematics? We change things in a correct way, but we don't change them just because we're human. That's not permitted, unfortunately. So now this is actually quite important. We've used this concept many times during today's lecture. E to the x is positive. Okay, so the square root of e squared plus 1 is actually greater than e. And so the negative would never work. So we have to discard negative radical. Basically because we're looking for real solutions, because since e to the x is positive. So this implies e to the x. It is amazing how we can use what we know about our functions to create some really good mathematics here. And then when you get to calculus, you're going to feel like you know you can conquer the world. So now we have e plus the square root of e squared plus 1. now we're done. We just need to solve for x. So what's a logarithm? It's the power of the base. So the power of, in this case, the power of e that equals this number is x. So x is a logarithm. It's a natural log. So x equals the natural log of e plus the square root of e squared plus 1. And that, ladies and gentlemen, is our solution. So the beauty of this problem is that I wanted to introduce a technique of converting an equation to quadratic form. This is a standard technique in mathematics. Because we understand the quadratic equation and its theory, any equation in quadratic form can therefore be solved. And so now when we write the solution set, we have the natural log of e plus the square root of e squared plus 1. And like I said before, this is actually given a symbolic name. It's called the hyperbolic sine. Sine hx, which is very different from the sine that we're going to study in this class. This is called the hyperbolic sine. The hyperbolic sine is also one-to-one. I have an algebraic proof of proving that it is one-to-one, which uses this technique. It's kind of interesting. Colleagues and others always ask me, well, why don't you just write a book? I'm like, well, the book I share with my students. And the idea is that as future STEM professionals, you will, in essence, write a book in your life. You will write down experiences and things that you do in your work as a STEM professional and compile basically a book. So what I want you to do now is to spend some time on these sections of the logarithm and exponents, which culminate basically with the equations as we've done here. And then next week, we will talk about some of the more distinguished models having to do with radioactive growth and decay, or actually just instantaneous growth and decay, radioactive growth and decay being a special case, and also Newton's law of cooling. So we'll work with those models. And then once we do that, my friends, we will be done with our review, and we will start with trigonometry in the unit circle. So the fun that we have had with reviewing college algebra will then therefore be over. And so we'll be hitting trig. It'll start from the beginning. So if you've never seen it before, it doesn't matter. It will be completely foundational, but it will move quickly, and it will prepare you for calculus. So I appreciate your attendance today. And if I see you at my office hours, my conference hours today or tomorrow, that'll be wonderful. Remember, I have that long session on Friday if you have some questions. And good luck as you continue to study. Enjoy this beautiful weather. It was so nice this morning to get out and run, and it was 60 degrees. That's why we live in Houston, ladies and gentlemen. The weather is beautiful. As long as we don't get too much rain, we're fine. Everybody have a great day, and good luck with your work. Bye.
Have a good day, sir.
You too.
See you.
Bye.